Previously, we introduced a new framework, which is built around the concept of a random variable. We already discussed the discrete random variables. Next, we will focus on continuous random variables. Let's recall the definition. A continuous random variable is a random variable whose all possible values form a continuous interval. For example, the following variables are continuous: the income of a randomly selected household, the lifetime of a randomly selected machinery, the wait time in a drive-through of a randomly selected customer, the incubation period of a virus for a randomly selected patient, and there are many other examples. Let's summarize everything that we know about discrete random variables and see what can be used for studying continuous random variables. Every discrete random variable X has a probability distribution table and a probability histogram. Using the probability distribution table or the histogram, we are able to find the probabilities of events in the form of an inequality that involve X. We're also capable of finding and interpreting the mean and standard deviation of a discrete random variable. We want to be able to do the same for any continuous random variable, but right away we run into a problem. The fact that it is impossible to list all values of a continuous random variable makes it impossible to construct a probability distribution table. So instead, we're going to focus on the visual representation of the information about the variable. An analog of a histogram for a continuous random variable is called a probability density curve. A probability density curve is a curve that has the following two properties. It is always above or on the horizontal axis, and the total area under the curve is equal to 1. For example, let's determine which of the following curves are the probability density curves and which ones are not. Let's find out if the graph of the following equation is a probability density curve or not. Since a part of the graph is below the x-axis, the given curve is not a probability density curve. Let's find out if the graph of the following equation is a probability density curve or not. Since the graph is entirely above the x-axis and the area underneath is equal to 1, you can verify that by using the formula for finding the area of a rectangle with the base length equals 4 and the height 1/4. The given curve is a probability density curve. Let's try another one. Let's find out if the upper half of the unit circle is a probability density curve or not. The graph is entirely above the x-axis, but the area of the half of the unit circle is not equal to 1. You can easily verify that by using the formula for finding the area of a circle with the radius 1. The given curve is not a probability density curve. Finally, let's find out if the graph of the following equation is a probability density curve or not. Since the graph is entirely above the x-axis and the area is equal to 1, you can easily verify that by using the formula for finding the area of a right triangle with the base equal to 4 and the height equal to 1/2. The given curve is a probability density curve. Next is the most important definition in this and the following chapters. We say that a continuous random variable x has a given probability density curve f of x if the probability that x is between a and b is equal to the area under the curve between a and b for any values a and b. We introduce the following notation, which will stand for x has the probability density curve f of x. In other words, if x has the probability density curve f of x, the probability that x is between a and b is equal to the area under the curve between a and b for any a and b. Note that in general, it is not always possible to find the mean and standard deviation of a continuous random variable. But when it is possible, we would interpret the numbers the same way as we did for discrete random variables. That is, we would use the 3 standard deviations rule to decide which values are expected, or likely, or unlikely to happen. discussed the differences between the discrete and continuous random variables and what effect these differences have on how we're going to work with continuous random variables.